record button because I almost forgot in the morning for my Chemi class. Yeah, I just hit the record button. So yeah, so spring is going to be virtual. Unfortunately, that's bad news. But then we better be safe than sorry. I have a feeling that the vaccine is probably going to happen sometime in 2021 because I've been in pharmaceutical industry. I know what happens in clinical trial, especially the clinical trial, phase 3 clinical trial, where they do a efficacy test in a large population of people, like it could be 15,000 placebo. Placebo means they're not getting the vaccine, and another 15,000 people who are getting the vaccine, and then they will do statistical analysis if there is any funny business going on in the study group that's using the vaccine. If they're feeling better, if their chances of getting COVID-19 is reduced, then the vaccine is working. If there are more significant deaths in the study group that's using the vaccine, then that's a red flag. That can happen too. So it takes a long time. It's not like this, the way some of us are trying to push and portray. Getting a drug out usually takes about 10 years. Getting a vaccine out probably takes less time because in general, the three clinical trials, phase 1, phase 2, and phase 3, they're supposed to be serial. This gets done, then you start phase 2. This gets done, then you get phase 3. So now they're overlapping. While phase 1 is going, they're starting phase 2. While phase 1 and phase 2 are going, they're starting phase 3. So because of the rush, right, we need to figure something out. But I hope it works out. I hope things get better. I think the death rate is dropping, so I think it's getting better. And even though everybody was predicting that it will get worse in winter, I don't know about that because it may not. Because if it was supposed to get bad in winter, that means the temperature has an effect on the virus, right? That means in the summer it would have gotten better. It didn't. Summer did nothing to this virus, its propagation and spreading and rate of infection. So from that data, if I'm making an intelligent prediction, my prediction is that in the winter it may not get worse. It may be taking its own course of time to recover and get better. I think, I hope I'm right. I sincerely hope. I may be wrong. But my hope and my prediction is that it may not get significantly worse in the winter because it didn't get better in the summer. From that, I'm kind of extrapolating. There could be another factor. Who knows? Maybe I'm missing it completely. So that's my hope. I hope that by summer of next year, by that through spring, we will probably slowly get out of this situation as much as we can. But we will probably be continuing to use mask and all of that stuff for maybe longer, maybe through 2021. In a very realistic estimate, it's probably going to be like in another 2 years before everything becomes almost normal. Who knows? Who knows? I'm not trying to increase anxiety in your minds, I hope. I'm just trying to give you a realistic picture, but then just hang in there, get used to it, do something fun, pick up a hobby maybe, that something that you can do being safe, painting, listening to music, playing a musical instrument. Somebody actually has started doing that. Didn't one of you weren't you saying that you're trying to learn some musical instrument? I don't know, someone in this class or somebody else was telling me that, oh, I'm just trying to teach me how to play whatever, some instrument. Do something in your garage, whatever. Any questions, any concerns before we start talking about the crystallization? I want to just go over some basic concepts because sometimes even my research students are sometimes clueless, like, oh, how do I go about crystallization? Okay. And then while we talk about that, I'm going to talk about the properties of solute, like a solid being dissolved in a liquid and a solvent. How does it play out? So I'm glad that we can cover that a little bit, cover the crystallization, and then I can take some questions about the assignments. Straight questions. I don't care if you get the answer from me. All I care is you learn the concept. That's all I care. And then I can always judge you judge you or test you in the exam. So there's nothing wrong. I mean, I don't have to lose my sleep that, oh, it's not right, it's kind of cheating because the instructor is giving away the answers. That's fine, but I can get you in the exam. I'm not going to get you in the exam, but I'm just saying phrase, figure of speech, that I'm not worried about that. I care, I trust you, and I believe that you will reciprocate and you will learn the concept. That's the whole idea. That's what I care for. Okay, I'll shut up for like half a minute. Any questions, concerns? When I'm in a meeting and I'm bored, then I do this. And sometimes my other people can see me that I'm getting, my OCD is kicking in. So I'm trying not to do that. I'm not bored right now. We have faculty meeting today at 4 o'clock. Sometimes I will do it like under the table. And they don't know what I'm doing. I'm actually spinning it because I'm kind of getting bored trying to solve unsolvable problems in our faculty meeting. I have many problems. I have lots of problems up here. No? Anything? Who had the best breakfast this morning? You want to talk about it? 5-course meal, like a breakfast burrito with a dessert on the side, with a great drink, like a smoothie, and some hash browns, and then, oh man, it's making me hungry. Yeah, good. You can always stop me, and I will always appreciate if you keep your cameras on. Okay, I'm switching to the board.
I just have one question.
Yeah.
For the assignments, we just have to do what's on Canvas, or do we also have to include like a report, like with the intro and the conclusion?
Yeah, just follow the guidelines for doing the assignment. I don't want you to get too hung up on the format, okay? Don't miss these important points. Don't forget to put your name on the assignment, okay? You can even do this. You can even like write on a piece of paper. You can do your answers on a piece of paper. Make sure you write Chem 129A, Fall 20, S Mitra, so that I know who you are. And then your name must be there and legible. Print it. And then you can answer like assignment question number 1 from chapter 2 in Pavia, and miscibility question, immiscibility questions, solubility questions, blah 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 blah. Just you can answer them, write them down. This is the simplest thing you can do. You can do it online. You can do it on a Word file. Okay, that's good. That's great. If you want to do that, that's fine. If you do not want to do that, if you're having trouble doing that, in case something is not working, you can do the old-fashioned way, write it down on a piece of paper, take a snapshot of it, okay, and you can attach it to an email and send it to me. You can send it to me. I prefer that you email it to me. Okay, you have my email address, smitra@mail.fresnostate.edu or smitra@csufresno.edu. Either one will send it to my inbox. Okay. I prefer that you don't upload it on Canvas. Maybe I'll send you guys an announcement, because sometimes it's more pain in the neck for me to extract it from Canvas than just downloading it from my email. I'll download it, I'll grade it, and I'll send it back to you individually. Okay, I'm not going to share it with everybody else. Then I'll give you a grade, and it's going to be posted. Okay, that's how it's going to be. For the quiz, I think I'm going to adopt a very similar. For the exam on coming week, I haven't decided whether it's going to be on Monday. It's not etched in wall. Maybe I'll take your feedback and we'll take the final decision about the scheduling it, depending upon what's going on for you guys in the next week. If you guys want, if you have a compelling reason to have it on Wednesday, that's fine, but it has to be Monday or Wednesday, one of the 2 days. It's probably going to take like an hour to do the quiz, and it's going to be timed. So you'll have limited time to do the exam, because I don't want to open it up for like, you can finish it in by the weekend. I'm not going to do that. Okay. You need to be prepared. This is going to kind of force you to learn the concepts that we have covered so far in these classes, using different types of learning materials, including videos. I think I'm going to adopt to videos as far as doing crystallization. If I have to show you crystallization, how to set it up in the lab, it's just going to be very complicated. I was thinking about that. I'm looking at different resources right now. I'm kind of doing my own research. I like some of there's a company called Labstar. They have some really cool videos. There are some Jove videos about recrystallization and crystallization. So I think there are already some in the module from Dr. Mohalski. I might add a few more there, add some links and some videos, YouTube links, and they're pretty good. They're really good. Some of them have become really good. So we may not have a class. I may not want to meet with you guys on Monday, or we can meet with you guys on Monday and do like a review if we're doing the exam on Wednesday. If we're doing the exam on Monday, then we can discuss it maybe today at the end of our lecture, like after we cover solubility, crystallization, and then I take your questions about the assignments, then we can discuss it. If it is too much, it's going to be probably 2 hours from now. By 11, you might be like too tired. If that's the case, then we can discuss the exam after we discuss these two items, the solubility, crystallization, and your questions and concerns about the assignments. After we do that, then we can have a two-way discussion about the exam. It's not etched in stone, but I want to get it done next week. Exam one should be done by Wednesday. Okay, but it's kind of flexible right now. Any other questions?
So are we going to talk about the assignment later, our questions, or do we ask them now?
I want to talk about the assignments a little bit later. Why? Are you in a hurry?
No, I was just wondering like when you wanted us to like ask questions.
I want to talk about something that I have in my mind first. Solubility, solute going into solution. Talk about that, talk about crystallization, and then I'll take your questions. How about that? Sounds good? Anything else? Any other concerns, anything else about this course?
A reminder, when is the exam?
As I said, we haven't decided yet, either Monday or Wednesday. I prefer to have it on Monday, but if you guys insist, then we can push it to Wednesday. It's not going to affect me in either way. Anything else? Okay, so let's switch to the other camera. The camera does go berserk, and sometimes it screws things up. It doesn't focus properly. So if it gets out of focus, then let me know. This is, we were discussing right before hybridization. I'm going really slow in that class. Okay, let's go. I am recording, yeah. At least when I do this, I feel kind of alive instead of just asking you guys to learn everything on your own. And once again, attendance is optional. I know that some of you, how many of you are there right now? 16 minus 1, 15. Yeah, okay. One person cannot make it today because she's having some family concerns, and she did email me. But again, I mean, at any time, if you feel like quitting, that's totally fine. I'm not going to be hurt. You're not going to hurt my feelings. And I know that this is very strange and weird time. Unfortunately, it's going to drag through spring. I have no idea how Thanksgiving and Christmas is going to be this time. We usually drive down to Irvine every Thanksgiving and have dinner with our old boss in UC Irvine, with whom both my wife and I did postdoctoral research. But I highly doubt that we're going to be eating turkey in his house on 25th of November. I highly doubt that. Will the turkey be virtual this year? So they will have good time they will be alive. Maybe. Let me just wipe it down with a piece of paper. I want clean board. Okay, so again, I wish we could show it to you guys using some real life lab experiments. But I have identified some videos on Labstar and Jove and some other university websites. There is one from, I think, Michigan or Minnesota. They're pretty good. So I'm going to share all of that as soon as I can. And also, like, I will try to have like a review session before the exam. All right, who we are? We are blue, green. We're not blue, green. So we are Chem 129A, fall 20, and this is a Monday, Wednesday class. Yes, Micra, and today is 9/16/20. Okay. So we're going to talk about solute what color should these two do when you mix green and let's say that when we mix purple and red, it becomes blue. It doesn't, but then let's just assume that. Okay, solute and solvent, and then we have the third thing, which is a solution. I want you to really understand these concepts. Okay, I'm going to ask you guys questions. So don't write anything on the Zoom because on the chat, because I'm not looking at the chat. Don't give me thumbs up or thumbs down or send me a signal with your hand gestures, because I want to hear you out. Okay, I think the volume is pretty loud. Okay.
The board is blurry right now.
Board is blurry. Okay, thank you, Elizabeth. So all I have to do is cut me off and then bring me back. Now it's okay. I think this camera tries to focus me, and then it puts it out of focus. Okay. Solute, solvent, and solution. Who knows what that means? It's simple, right? Let's say you take you're making lemonade. Okay. You're mixing something with something else and you're getting lemonade. Which one is the solid? Which one is the solute? Which one is the solvent? And what's your solution? So let's use the lemonade example. So lemonade, I'm not going to drop any hint by using color. I'm going to really try to not help you here. So in lemonade, is made out of something and something else. To use only the black color. I don't want to help you. So what's a solute, what's a solvent, and what's a solution? You can use an example and explain. Somebody explain. Sooner you participate and volunteer, faster we can proceed. Cover more material. That's going to help you with assignments. That's going to help you with the exam. I want all of you guys to do well in the exam. I'm spending so much time, so do it. If you don't care about your own grade, do it for me, to have a better life through the rest of this semester. I'm just kidding. You should do it for yourself, for your future, for your career, for your soul, for your self-confidence, and for your, because you deserve it. That's why, nothing else. Anybody? Use an example. Yeah.
Go.
Who wants to answer? Let's see. Maybe you can say that I'm ready to answer. Elizabeth?
Can I answer?
Absolutely. Good, Tej.
Yes. So the lemon would be solute, and then
Lemon juice, let's say lemon juice and sugar. Okay. Okay, there is in lemonade, there is lemon juice, sugar. Let's keep it simple. Lemon juice, sugar, and what?
water
Water.
as solvent. Yes.
Okay. So lemonade is something. Lemon juice is something else. Sugar is something else. This is actually a good example. I really like how you started because I was not thinking about the lemon juice, Gurtej. Okay. You cannot answer. I'm forbidding you. Somebody else. Pick one from here. Let's say this is 1, this is 2, this is 3, and this is 4. Okay. Somebody else pick one of them and tell me whether it's a solute or solvent or solution.
The water
Water.
is a solvent.
Oh, sorry.
Okay, you're done. Water is a solvent.
Dr.
Water-
Mitra, the board's a little blurry again.
Darn it. I need to figure out how to like lock the focus of this camera. I can. I mean, Zoom doesn't allow me to do that. It's still focused or it's out of focus. Give me a thumbs
No,
up.
it's good now.
That looks
Good
better.
now, right? Yeah, it's good now. Okay, I'm going to just stick to the board so that it doesn't get screwed up. So one answer, I think it was Shireen. Water is solvent. Somebody else, don't give the answer. Just say that. Can I go or make some noise so that you're on my screen? Camille, you wanna?
Yeah, can I answer this one?
Yeah, you can answer. Which one you want to answer?
The lemonade. It's
Lemonade. Lemonade is what?
the solution.
Lemonade is the solution. Okay, you're done, Camille. Somebody else.
I'll answer for sugar.
Okay,
Sugar is a solute.
sugar is a solute. Okay, and lemon juice. Somebody else. Purple pen.
Lemon juice is also a solute.
Thank you. That's Elizabeth, right? Yeah.
Yeah.
I'm getting the hang of your names. This is really weird. I now I understand when you youngsters like you guys are spending so much time on Instagram and Twitter and Facebook. You know, it's a weird virtual reality. I don't know. I still like the real human interaction. Solution, solvent, solute, solute. There are two types of solute. This is very interesting. I love it because one solute is a liquid, one solute is a solid. They're still solute. Usually, sometimes we are wired or we are preconceived or we are biased to think that solute means solid. Solute doesn't mean solid, right? So the bottom line is solute and solid they mix and then they produce a solution, right? It's as simple as that. Now, water happens to be the solvent here, right? Water looks like this. Water is the solvent, so I'm going to write it in red color. If this is water, okay, you know that the two major bonds, the one major type of bond that water is capable of doing is it can do hydrogen bond, right? So whatever it's dissolving, it's going to be capable of making hydrogen bonds with, okay? So once again, this is, hopefully it's going to help you with your Chem 128A and 128B. Electronegativity values Okay, electronegativity values, it's the love of an element to pull the bonding electrons toward itself. For oxygen and for hydrogen, these numbers are 3.5 and 2.1. For carbon, it's 2.5. For fluorine, it's 4.0, pretty high. For nitrogen, it's roughly 3.0, right? So this bond, this guy is pulling the electrons, these electrons toward itself with strong power, okay? The difference between these two is 1.4. That means this bond is polar covalent. We have discussed it in the past. This bond is a pretty polar covalent bond, and it's being pulled toward oxygen. Okay? And as I have told you that unless it's an ionic bond, it's a crime to write this. Minus charge and positive charge. You cannot do that. You just cannot do that. Okay? Because it's not an ionic bond, it's just it's a very polar bond. Once again, covalent, sorry. Non-polar covalent bond electronegativity difference is 0 to 0.5. Okay? Polar covalent bond, the electronegativity difference is 0.5 to 1.9. And ionic bond, 100% ionic, is greater than 1.9. Okay? So this bond, by being here, it's a polar covalent bond, and all we can do is we can do this. We can say it's delta minus minus, delta plus, and delta plus. That means it's kind of generating like a little charge separation. If I would write this molecule, I would probably put the bonds kind of like that. If I want to do like a cartoon picture, okay, the bonds are more toward oxygen than hydrogen. Okay, so that's the deal. Okay, the lone pairs are there, and the lone pairs are really awesome to make hydrogen bonds. They can do really great hydrogen bonds. So they're capable of doing H bond. H bond, it's going to be an H bond acceptor, and this is going to be an H bond what you're learning now, if you remember some of it, it's going to help you with biochemistry and organic chemistry both. They're going to talk about, in biochemistry, they're going to talk about hydrogen bond donor and hydrogen bond acceptor, okay? Because you need a hydrogen from another source, so it's a hydrogen bond acceptor. When you have a hydrogen with the right setup attached to an oxygen or nitrogen or fluorine, then it's a hydrogen bond donor. Okay, so water molecule is not only capable of hydrogen bond donor, it can donate a hydrogen bond and make a bond molecule, make a hydrogen bond with somebody else. It can also accept hydrogen bond from a hydrogen bond donor somewhere else, and not just one, two of them. So water is perfect because it is capable of donating 2 of its hydrogens for hydrogen bonding, and it is capable of accepting 2 hydrogen bonds from other hydrogens. So it's like it's capable of hydrogen bonding everywhere. In the middle of it, you know, if you think about it's like a V. The V, the corner of the bent part of the V can do 2 hydrogen bonds with 2 other hydrogens from somewhere else, and these 2 guys can do 2 hydrogen bonds. So that's why water is such an awesome solvent for polar ionic compounds. Non-polar compounds, good luck. It's not going to dissolve. Like hexane, not going to happen. Ether, not going to happen. I'm going to talk about ether and talk about something else there, okay? Something very interesting. That could be a perfect question for the exam, but I'm going to talk about it because I just remembered. I have to let it out, okay? Otherwise, it's going to be an itch in my brain until I give you guys the exam, okay? So far so good. You guys are absorbing this material. Solute, solvent, solution. We used an example of water, and I'm kind of like, this is an universal solvent, whether you remain as a chemist, whether you become a doctor or pharmacist or ophthalmologist or teacher at various different levels, starting from kindergarten to university. This is important knowledge for a human being to know. Okay? We are going to be dealing with water all the time. If you're popping a tablet and if you realize something went wrong, you can actually think like, maybe it was not soluble in water. When we are doing a drug development, sometimes the chemists are thinking ahead, that making sure that the molecule that they're trying to develop as a drug or whatever is actually water soluble. Then it's going to be an oral drug. If it is not a water soluble molecule, then it has to be an IV drug or some other drug. And that's more pain, that's more cost to develop. Water soluble oral drug is better, and it's going to be more popular because you can pop the pill or the capsule and drink it with water. This is extremely important, right? So you got that? We got that down. This is the little bit of the theory we have already covered. You have seen it in other classes. So there's nothing new. I mean, those of you who are getting bored, please don't get bored. Just be patient. Okay, so that's that, right? Sugar on the other side. Sugar, I don't remember the exact sugar. Sugar chemistry is the hardest organic chemistry. Sugar has bunch of cyclohexane rings. I'm just going to write it as cyclohexane or cyclopentane, okay? And they have many hydroxide groups. Okay? They also have groups like this. There is stereochemistry involved. Stereochemistry involved means the group can be up or group can be down. I don't want to get into that because I love stereochemistry and I can get really distracted and talk 3 hours about stereochemistry. You don't want me to do that. Okay. This wiggly line, just a little tip for you guys when you get to stereochemistry. Let's say there is a molecule, and this molecule can have a specific group, a hydroxide group up. That wedge means out. The wedge means it's sticking out like that, and the hydrogen is down, okay? Let's say there is another compound where the hydroxide group is down behind the whiteboard. Then the way we write is we put that dashed line on the hydroxide bond and put the hydrogen up. Now let's say you are dealing with a molecule, cyclohexanol. Let's name it cyclohexanol, like ethanol. Cyclohexane, cyclohexanol. Ethane, ethanol. So just as simple as that. Okay. Let's say you are dealing with a compound that you have no idea whether it's up or down. In this case, it really doesn't matter both the compounds are same, but I'm trying to prove a point. Okay, I'm trying to teach you like a sign. If you do not know which way it is, up or down, we can always write with a wiggly line, like a zigzag, like a wave. When you write it with a wave, that means you don't know if it is out or in. As simple as that. Okay. So when it's wiggly line, that means I don't know. I don't want to specify whether it's up or down. Depending upon, for sugars like hexose and mannose and glucose and sucrose and all these guys, some of them are single units of different sugar. And then you have the polymers. Polymers are the macromolecules in our living system. When you are eating sugar from different resources, they're made from different starting materials. And these sugar chemistries are nightmares for organic chemists because one hydroxide is up, second hydroxide is up, third hydroxide is down, fourth hydroxide is up, fifth hydroxide is up. Okay, that's one kind of sugar. That's one kind of monomer. Up, up, down, up, up. Up, down, down, up, up will be another one. So you can have so many combinations, okay? Dealing with the stereochemistry, doing the chemistry with the right stereochemistry, up or down, it's really a nightmare. If someone has told you, or if you come across a chemist who has done like successfully sugar chemistry, you should, I am going to really bow and like show my respect to that person. Like that's if you can handle that, you must be a great synthetic chemist, okay? Sugar likes to dissolve in water. Give me a reason. Why does sugar love water so much? What's the reason? I'm just going to focus on one hydroxide group. Let's say it's got a bunch of hydroxide groups, and one hydroxide group looks like that. And this is what water looks like. We have already covered. You can just articulate it in like one short sentence. Anybody wants to tackle that? Why sugar should be so well soluble in water? So let's say this is sugar. I'm going to call sugar this way. I'm going to call it ROH. This whole thing, I'm calling it an R. R is like a representation of that whole business. Let's say this is R. When sugar sees a molecule of water, do you think they're going to hate each other or they're going to love each other? What's your gut feeling? What kind of bonding can happen between the two? Just answer that. Camille?
I'm sorry, can you say that again? I didn't hear what you said.
What kind of interaction will happen between a sugar molecule with, I'm just showing one hydroxide group. Sugar means bunch of OH hydroxide groups. When a sugar interacts with water, what kind of bonding happens between the two?
Oh, hydrogen bonding?
Hydrogen bonding. Is it going to be just one or going to be many?
No, it's going to be multiple.
It's going to be multiple, right? This can interact here. This can interact here. Okay? This can interact here. This guy can interact here. This guy can interact with another hydroxide of another sugar. Okay, this guy can interact with another water molecule. So it's endless. That's why sugar likes to go in water so easily. Okay, so I'm just trying to teach you guys the concept of how a solid or a liquid, not just to solvents. Well, liquid and liquid is kind of like what we did, but in this case, this is being treated as a liquid, as a solute, because you are dealing with small amount. You're not dealing with like 10 ml of one solvent and 5 ml of another solvent. You're dealing with like maybe like 0.1 gram of that and 20 milliliter of this. 20 ml and 0.1 gram. It's not really solvent. At that point, we say it's a solute. You're just trying to dissolve a little bit of lemon juice in that solution, in the water, okay, to make lemonade. So the bottom line is when you mix one solid in a liquid or one liquid in another liquid, the bottom line is there has to be something similar about them, okay? So dissolving, the concept of dissolution, dissolving solute, which could be solid or liquid, in a solvent depends on, I'm just using different colors, depends on how like they are. That's probably bad English, but the bottom line is there must be something similar between the two so that they can make a comfortable bond. If they're too uncomfortable with each other, if one guy cannot do any hydrogen bonding with water or is not polar at all, good luck, it's not going to dissolve. If it is polar, if it is even ionic, water is probably going to dissolve that guy, okay? So what we have discussed so far is solute, solvent, solution. We have taken an example of water. I really wanted to talk about water, getting a little bit deeper into the water and how water can interact. So my next step is to discuss how a polar compound, such as sodium chloride, common salt, can go into water. So I'm going to take a picture of the board. Since I came close, I might be screwing up the focus. If the focus is all gone through the window, gone with the wind, then let me know. Okay, I just took a snapshot. Any questions so far from here? If it is too simple, you can tell me. Maybe I can up the game a little bit and not get down to this basic, discussion. Maybe I can move away from this level of fundamental concept discussion. Do you think this is doing you any good or not being helpful? I don't want you to praise, or I don't want you to like throw things at me. That's the good
It was helpful.
Huh? Sorry?
It was helpful. Yes.
It's helpful? Okay. All right. So let's erase the board. Let's erase the board and let's stick with water and talk about something like what other things can dissolve in water and what things cannot dissolve in water. Let's get to the bottom of it. Okay. I'm going to still continue to discuss this business. Okay. I'm going to draw the water molecule one more time, and we'll go from there. And this is going to help us understand crystallization. Crystallization is something that I get very frustrated because after spending 2 semesters in the lab, 129A and 129B, students are sometimes still clueless. Like my students, like really smart guys, 4.0 GPA, 3.99. They don't understand what crystallization means, what mixed solvent crystallization means. Okay, I'm going to speed up a little bit. I cannot increase my speed like the way you can do it in. Let this be. No, you know what? If necessary, we're going to write it again. Okay. So another example is, oftentimes we make in the hot, humid, and hazy summer day, when I would come back from school, like all sweaty and tired and we used to have this wind called, the storm called Lou. Like the temperature would be 110, 105, 111 degrees in the city where I grew up in India. I would ride my bicycle back home. It used to be very dry. I would still sweat. Sometimes I would take an umbrella, wet the umbrella with water, and while I'm riding the bicycle, I would hold the umbrella so that the air passes through it and kind of cools me down. So when I would come home, my mother used to make, some of you guys who are from the same part of it, of the world, you will know it's a yogurt drink. And she would put yogurt in milk and a little bit of sugar and a little bit of salt. What is salt? And we dissolve salt all the time. All our food has salt. And most of our food is based in a solvent. That solvent is water, okay? Most of our food items are cooked in water, right? Some things are cooked in milk. I don't want to get started with talking about milk. Milk is an awesome stuff. Milk is the concept of milk. We'll discuss it some other day. Okay, I don't want to get distracted because it's going to be another long discussion. So water, since it's red, I'm going to continue to respect the color code. This is water, right? And this is important because the lone pairs help with hydrogen bond. And the hydrogens are also important because they help with hydrogen bond. So you can accept 2 hydrogen bonds from here. You can donate 2 hydrogens from here, okay? Now sodium chloride, it's common salt. So it can dissolve. The bottom line is this guy can dissolve, polar covalent. It's not the right description, but you understand. I'm going to say polar covalent compound. That means compounds that have polar covalent bonds. Okay, the number 1. What else can it dissolve? Can it dissolve something else? This is a universal solvent. Okay. So when you deal with common salt, let's draw common salt with black color. Common salt, we write it as sodium chloride, NaCl. Okay. It's important that you understand how the bonding happens in NaCl. I'm going to draw another compound on the side, okay, just to compare. Okay, hydrogen and Cl. HCl is another compound. Okay, NaCl is another compound.
I couldn't quite hear you. Could you please repeat?
Shut up. It's trying to outsmart me. NaCl and HCl, right? Sodiums, can somebody do a search and find out what the electronegativity of sodium is? I believe it's 0.9 or 1. Maybe one of you can just Google electronegativity of sodium and do me that favor. So hydrogen electronegativity of hydrogen is 2.1. You can unmute and tell me what it is.
For sodium, I Googled it and it said 0.93.
0.93. Okay, thank you. I'm just going to say 9.10. Okay. So if you look at the electronegativity values of these 3 elements, hydrogen is 2.1, chlorine is 3.5, sodium is 0.9. Okay. So the gap between these 2 will be 3.5 minus 2.1 equal to 1.4. That's the gap here. What does that mean? Is it going to be a non-polar covalent bond, or is it going to be a polar covalent bond, or will it be an Will it be a polar or will it be an ionic bond? Non-polar covalent, polar covalent, or ionic? Which one will be your answer? The gap between the electronegativity of hydrogen and chlorine is 1.4. So
Polar covalent.
polar covalent, very good. So this guy is going to be a polar covalent bond. Polar covalent bond, right? Sodium chloride, the gap is 3.5 minus 0.9 equal to what? 2.6. What does it mean? What kind of bond will that be?
Ionic.
Ionic. Let's get down to the basics. Okay, I know that we can actually continue this discussion on Monday after we hit 11 o'clock. I don't want to torture you for more than 2 hours. Okay, so wherever we are, we can stop at that point and we can resume the discussion on Monday. Okay, we are still in crystallization. You guys can watch the videos that I will share with you, and then we can come back on Monday and talk. So I really want to limit this torture for 2 hours. Okay, sodium is hydrogen, lithium, sodium in the periodic table. If you see the periodic table, okay, hydrogen, helium, lithium, beryllium. I'm going to go backwards. It's easier for me to write. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, chlorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. I don't remember some of those. That means in the periodic table, okay, this means that when you go down a column, they have some similar properties. What property does it have? Something is same for all the elements down the column or up the column. What's that? Number of something.
Valence electrons.
Number of valence electrons. Okay. How many valence electrons does hydrogen have?
1.
How many valence electrons does lithium have?
Also 1.
Sodium 1. Okay. Let's say carbon 4, silicon 4, boron 3, aluminum 3, helium 2. There's a discrepancy. Neon 8, argon 8, xenon 8, krypton 8. They're all 8, right? Chlorine, bromine, iodine 7, 7, 7, 7, 6, 6, 6, 6, 5, 5, 5, 5, 2, 2, 2, 2. Okay, that's the deal. Sodium is born with 1 electron, and the Lewis dot representation of sodium will look like this. So representation of hydrogen will also look like that. Chlorine looks like this. When chlorine is hanging out, see how we behave differently with different people. Electronegativity, 0.9. Electronegativity, 2.1. Electronegativity, 3.5. A really greedy guy hangs out with someone who's not really nice, not that giving, but not as greedy as chlorine. When they bond together, chlorine and chlorine and hydrogen come to a conclusion. They both like money, but they're, hydrogen is not that giving, not that unattached to money, and chlorine is not that crazy. It has to compromise. These guys decide to share. And they make a bond that's going to be shared, but kind of pulled toward chlorine. Okay? Pretty pulled, a polar covalent bond, right? When sodium and chlorine get close to each other, this guy is like a hermit. It has $10 in its pocket like hydrogen, but it really doesn't care. Like it wants the electron pair only 0.9 times than hydrogen. That's like 2.1. Like hydrogen is almost more than 2 times greedy for that bonding electrons. Therefore, chlorine cannot snatch it away. When these guys mate, this electron is basically snatched away by chlorine. Okay? When they get together, that electron from the sodiums, which level? This is 1s, 2s, 3s, level 3. As the levels go out and out and out, farther away from the nucleus, the pull from the nucleus, the attraction between proton and electron, that also fades away as the distance increases. As you go down, your love for the bonding electrons diminish. You become more and more like whatever. You take my electron. Who cares? I'll form an ion. I'll stick to you because I'm going to be a poor guy. I'll be completely dependent on you. Okay. So the sodium becomes totally stripped out of its electron, and chlorine gets hold of that electron. Okay. Okay. Chlorine feels like argon. It thinks, oh, look at me. I mean, I have 8 electrons. I am almost like argon. And this guy, sodium, loses that electron, and it feels like, I'm kind of looking like neon. They both feel that they're looking like the celebrities. Unfortunately, by completely losing the electron, sodium is no more a neutral sodium because it doesn't have that electron. It's sitting on chlorine's valence shell. Therefore, this guy has an extra proton in the nucleus. This dude has an extra electron more than the number of electrons number of protons it has in the center. Therefore, it's a negatively charged species. Okay, so we write sodium chloride as, this is probably very basic. You guys probably already know. I'm really sorry if I'm talking about something that's too simple. Okay, sodium chloride. So the bottom line is when sodium chloride comes in contact with water, how do they interact? Why is sodium chloride so soluble in water? Why does every darn salt in the whole world dissolve in water? Because of the following reason. When you have water, it's pretty polarized bond, extremely polarized bond because of the electronegativity difference, and you have 2 lone pairs. Okay, so this is delta minus minus, and this is delta plus and delta plus. Okay, when sodium chloride comes in contact with water, they have some kind of polar bond. It's not hydrogen bond, but they have like a polar molecule and an ion. That's also another type of interaction. They have that interaction going on. So sodium interacts with the lone pair, bonds with that, and this guy bonds with the hydrogen, which has slight polarity. So any salt, most of the salts, unless they have some strange behavior, they're kind of like non-polar salts. usually salts dissolve in water pretty well. So that's why water serves as a fantastic, universal solvent for not only polar covalent molecules, but also for salts. What is a salt? Salts have ionic bond. This is very important for you guys in organic chemistry for taking competitive exams like MCAT and DAT and TCAT and whatnot, okay? Salts have ionic bond. This might sound very trivial and very simple, but this is something that most of us tend to forget about solubility. So with that, I'm going to take a picture. I'm going to talk about crystallization a little bit and then start taking some questions. I'll see if I can finish the crystallization discussion quickly. We can cover it a little bit later, maybe on Monday again. Okay. I want to take your questions, but I want to talk about the crystallization just briefly. Okay. Any questions from what we discussed right now? So we basically discussed solution, solute, solvent. Solute can be liquid or solid. Solvent is a liquid. It cannot be a solid. This cannot be a solid. Solution is always liquid. It's a solution. So whenever you sometimes even like professors and postdocs and PhD people will use the words incorrectly. When you're talking about a liquid, it's not always solution. If it is a pure liquid, you are only talking about water, nothing else dissolved in it. If you're talking about hexane, nothing else dissolved in it, then it's a solvent. It's not a solution. So sometimes we misspeak. Like sometimes in India, we used to say AC current. AC current is redundant. AC means alternating current. DC current is redundant. DC means direct current. It's like, when Starbucks sells you chai tea. Chai in Indian language means tea. It's like TT. So that's kind of not really smart, but that's okay. We don't know what that means. So solution is 2 things or more. It could be 3 or 5,000 things in there. A solvent with 4,999 solutes in it, right? Solvent is pure, one liquid. Solute, solid or liquid. Okay. So we just discussed that. We discussed ionic compounds. We discussed polar compounds. We discussed non-polar compounds. We discussed what makes them polar and non-polar and ionic by taking their electronegativity differences. We pretty much covered that. And most ions, most salts dissolve in water. Many polar compounds dissolve in water. And so hopefully this is going to help you even with answering some of the questions in the assignments. So if you have no questions, I'm going to erase and start talking about recrystallization. I'm going to talk about the basic recrystallization, then I'm going to talk about mixed solvent recrystallization. Okay? Questions? Okay, I'm going to speed up a little bit, so let's keep going. So when it comes to recrystallization or crystallization, let's talk about simple crystallization first. Before we talk about crystallization, let's talk about something quickly. I just remembered that. Okay, I think this is also going to help you with the assignments. Okay, let's talk about a couple of different solvents. Yeah, then we can kill 2 birds with 1 stone. 3 scenarios. 3 scenarios. Okay, scenario 1. Scenario 2, black and red. When black and red mix, what color do we get? I don't know. I'll just say purple. You know what? That periodic table has to go. Sorry, periodic table. We have to go. I love these pens. I used to use pens from somewhere else. They were horrible. So we're going to deal with polar stuff here. And this is going to be our non-polar region. Okay, this is non-polar. That's polar, that's non-polar. This is in the middle. This is, we're going to call it intermediate. Okay. So non-polar, let's talk about some solvents that are non-polar. In the polar, I'm going to write a solvent that we're going to be using for dissolving stuff, water. Okay, that's an example of a solvent. An example of a non-polar solvent will be hexane, right? How does hexane look like? Let's break up one of the ends. Explode the end. CH, electronegativity 2.5, electronegativity 2.1. Pretty non-polar bond. So this means non-polar means greasy. This is a pretty darn greasy compound. We always use the word greasy. That means if you have grease in your finger, you cannot wash it with water, right? You got that right. Understand that, right? Someday I'm going to talk about micelle and soap. How does that work? That knowledge is going to be very critical for your doing well and understanding many biochemistry concepts. Not so much so in organic chemistry. We just kind of touch upon that. But that's that. We'll talk about it later on, okay? So let's say now we are trying to deal with some solutes, okay? Trying to dissolve something in here. Let's say we are trying to dissolve something that is made out of carbon and hydrogen, something like this. How about, you guys know how benzene looks like, right? You may not have studied it yet, but benzene is, let's use cyclohexane. Let's forget about benzene. This is cyclohexane. Okay, this is cyclohexane. So I'm trying to test it in non-polar solvent like a hexane, 1, 2, 3, 4, 5, 6. This is my solvent, this is my solute. So I'm taking maybe a milliliter. Let's say we have a test tube and you have a whole bunch of hexane, like 1 or 2 or 3 ml. Then I'm going to put this guy as a drop. Let's use a different color. Let's change the color of the solute. Okay, this is cyclohexane. I'm going to put that as a drop. Okay, the cyclohexane is going to go in hexane as drops. And again, you have a little vial or test tube filled with water. Okay, that's water. And then you're testing a solute. First solute is cyclohexane. Okay, you're dropping it in the cyclohexane. Okay, got it? So far, so good? Okay. What will be the outcome of dropping cyclohexane in hexane and cyclohexane in water? Let's deal with one thing at a time. What do you guys think will happen? Will cyclohexane dissolve in hexane and make one clear liquid? It's not going to float on top of it or sink at the bottom. Insoluble means sinking at the bottom or floating on the top. Soluble means, so the question is, this is the question: soluble or insoluble? Only two things can happen. Same question here. Soluble, insoluble. Okay, answer this first. So make sure that you can make some noise like I'm ready to answer, and then you can answer the question. Is cyclohexane going to be soluble in hexane? Question answer A, answer B. Who wants to answer it? Like dissolves like. Let's write down. This is in the Bible of organic compounds. Like dissolves like. Birds of the same feather flock together. The same concept. Birds will not be hanging out with crocodiles. Well, sometimes they feed off of their teeth. That's a different story. There is some similarity. There is some vested interest. So, cyclohexane and hexane, soluble or insoluble? What do you guys think?
Soluble.
Soluble. Why? What kind of bonding will happen between the two? Who can answer? Gurtej, you are forbidden. You also already answered. I'm just kidding. Anybody can answer. You can answer. What kind of bond will happen between carbon-carbon, carbon-hydrogen, and hydrogen-carbon?
Wouldn't it
Yeah, go ahead. Come in.
just non-polar bonds or like Walden inversion bonds?
Yes.
And
There
then
is
just like-
another word I used because that's how I kind of grew up, learned it. What is that word called? Like the European name with the first name with
London
lowercase?
inversion?
Van der Waals force, right?
Oh, Van der Waals.
Van der Waals. That's good. Okay. What's going to be the outcome? Soluble or insoluble? Cyclohexane dropped in water.
Insoluble.
Elizabeth, very good. There's nothing common between them. No, it cannot hydrogen bond. It's not polar. This guy cannot do any Van der Waals force or like whatever dispersion force you guys call it here. Sometimes I have, my brain doesn't want to learn some things. So there's nothing that can happen between the two. They're very unlike each other. It's like one guy is extremely introvert and another person is extremely extrovert. Okay. Sometimes there can be bonds, but in this case it doesn't. So yeah, that's right. There's nothing common between them. Let's analyze a few other compounds that might give you some ideas, like what kind of organic compound. This is going to be really helpful for you guys to basically predict the answers for the assignments. Okay, the compound. Let's talk about different kinds of compounds. Yeah, I think I'm going to end my discussion with this. Different types of organic compounds. Okay, one type of compound is, you know what, we need more space. So I'm going to just erase the top. What was written here? Like dissolves like. It's not that important. Okay, I'm just going to say organic compounds, different types, and I'll try to drop some hints. Like, what do you think will happen? Will it be dissolved in non-polar compound or polar compound? An intermediate compound will have polar group and non-polar group. So intermediate solvent will have something greasy on one end and something non-greasy on the other end, polar end on the other end. Can somebody predict what kind of an example will fit in this purple box that will have greasy property and non-greasy property?
Like soap?
Yeah, sure, but you are thinking too ahead. Stay within our boundary right now. Soap is very non-polar at one end and a little polar group at the other. That's perfect, but something simpler, something that we we really enjoy drinking on Friday evenings sometimes, unless you're prohibited or underage.
Like, what do you call it again? Alcohol?
Alcohol, that's right. Alcohols have this mixed properties. Okay, so this end is polar, this end is non-polar. Okay, we love them in the lab because sometimes they offer awesome properties for recrystallization. Okay, this is kind of an intermediate. They have non-polar end and a polar end. And what Camille was talking about, he was talking about soap or fatty acid salt. Fatty acid salt means this is fat. Extremely long fatty acid, like a hydrocarbon chain. It could be carbon, I don't know the exact number, but it can be up to like, the number of carbons could be as long as like 25, 30, okay? Something like that. I hope I'm not too wrong. Okay, and on the other end of it, you have a very special group. Let's put it down here. Other end of it, you have a carbonyl group, which is pretty polar because it's pulled toward this direction with a double bond. And on the other side, you have an oxygen and a hydrogen. And this functional group is called, who knows what this group is called? COOH. Most of you know it. Vinegar, chips, formic acid, the ants inject you with, that burns, benzoic acid, formic
Carboxylic acid.
It's a carboxylic acid. This is the carboxylic acid. Okay, so this is very polar. More polar, more than OH. More than just a hydroxy OH. Because you have the carbonyl group. Carbonyl group will make this hydrogen so loosely bound that it gets knocked out very easily. Okay, that's why it's an acid. Acids can donate protons. That's a different discussion. I don't want to talk about it right now. So this is like a micelle. Sometimes it's shown as like a tadpole. This is the greasy part. With a polar head on the other side. Okay, in this case, it can be slightly negatively charged, and sometimes it comes with a salt, sodium salt, to neutralize it. So they're usually shown as a micelle. And soaps are made out of micelle. That's a great example of something that's got polar group and a non-polar group. But it's going to foam, it's going to froth. We cannot use it as a solvent. Okay, so that's a great example. Okay, organic compounds, alkanes, non-polar, alkenes, non-polar, alkynes, non-polar. They're all non-polar. Obviously, that's going to be slightly more polar, slightly, but the electronegativities don't change. This is going to be slightly more polar, okay? So then after that, we get alcohols. I'm going to write down alcohol in blue color. This is also going to be a good review for you for different functional groups. So these guys, all these black compounds, alkene, alkane, and alkyne, they are hydrocarbons. Okay, alcohols are alkane chain with an OH. That could be ethanol. That could be methanol. That could be rubbing alcohol, isopropanol or 2-propanol. It could be butanol. It could be, again, this stuff is going to be very helpful for 1, 2, 3, 4, 5, 6, 7, 8. Octanol for your quizzes. Now, these guys are polar. They're polar by virtue of having the hydroxide. But you're kind of screwing things up by increasing the nonpolar chain. So the propensity, let's do a little exercise right here. If I ask you, this is very interesting. Okay, this is very interesting. This will go hand in hand with your assignments. If we pick methanol, the atom of the baby alcohol, like baby Yoda, okay? Methane is baby alkane, like the smallest alkane, right? The smallest alkane is methane. The next alkane is CH3, ethane. Then propane, then butane, then pentane, then hexane, blah, 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 right? That's the baby alkane, like baby Yoda. This is the baby alcohol, okay? The smallest, the cutest alcohol, not really cutest, because if you accidentally take it inside your system, you can go blind. It makes you blind, okay? This guy is pretty good, ethanol, nobody's gonna argue with me. Isopropanol is good when you have to rub someone the wrong way. Make sure you carry some isopropanol, the rubbing alcohol with you. Butanol, octanol. Some questions. Okay, let's answer. This is like now we are starting a review. How many of you are there? 1, 2, 3, 4, 12, 11. That's fine. Okay. Water solubility. If you're trying to dissolve these guys, methanol, ethanol, isopropanol, butanol, and octanol. I don't know some of the exact answers, but we can guess. Okay. We already did some of the experiments in the lab the other day. We tested, I think, this guy, and tarbutanol. We tested this one the other day. We tested that, and that in water. So when you take methanol in water, do you think they will dissolve or not? What is your gut feeling? Methanol and water. Soluble or not? S for soluble, I for insoluble. Methanol and water. Use your concepts, what you have learned so far. What can they do between themselves? What kind of interaction they can have? Not James Bond. What Bond? Speak up. What kind of interaction may occur between methanol and water?
Hydrogen bonding.
Hydrogen bond. So will the methyl group be causing too much trouble, or it's kind of a small greasy part? What's your answer? Soluble or insoluble? These two.
Soluble.
Soluble. Okay. Let's take this guy and water. Soluble or insoluble in water? So this is soluble. How about this? Ethanol and water. You already know. Soluble. Isopropanol and water, we tested soluble. Tarbutanol and water, it had trouble. So I'm just going to say, I'm going to put like a wiggly line, the AC sign, the alternating. I'm going to say soluble. Butanol is probably going to be, yeah, soluble. What do you guys think about octanol and water?
Insoluble.
I think so. It's almost like a micelle. It might form like a soap, but probably not. Okay. Now let's go back to, let me ask you this question. I'm going to use one color. Methanol, ethanol, butanol, propanol, butanol. I don't know what all is this, and then I have no idea what I drew. Let's call them 1, 2, 3, 4, 5, 6. Between the 6 alcohols, you just pick the number. Which alcohol may be soluble in hexane? If you have to pick one alcohol from here, methanol, ethanol, propanol, butanol, pentanol, nonanol, let's make it decanol, which alcohol will be most likely to dissolve in hexane? Hexane,
Decanol.
sorry?
The decanol.
Hexane solubility, most likely decanol. Why did you choose that answer, Elizabeth? If I ask you to justify your answer. That's the right answer.
The like dissolved like.
The greasy chain, the greasy part. The alcohol is going to cause trouble. The greasy, it's alcohol is common. It won't like to mingle with hexane. But you're making things better for something to go into hexane by increasing the grease. Maybe not enough, definitely not enough. Not enough. Maybe partially soluble, I don't know the answer. Maybe partially soluble, but this guy will probably have its best chance in dissolving in hexane. You got it? Everybody? Okay. Some other solvents that are going to be polar or non-polar. So I'm, instead of talking about solubility, let's talk about some other compounds. We are continuing to discuss different organic compounds, what makes them polar. Okay, we covered hexanes. We covered alkane, alkene, alkyne, alcohols. So the bottom line is the hydrogen has to be attached to something like an oxygen or nitrogen or something like, I don't know, sulfur stings. So I'm going to put it in this color. Sulfur, that kind of, so whenever you have a hydrogen attached to one of these guys, polar species, then this hydrogen makes the molecule polar. Okay, whenever you see a hydrogen attached to an oxygen or nitrogen or sulfur or, I don't know, phosphorus, these guys are pretty polar because now it can, especially with these two, it can hydrogen bond. This hydrogen is capable of hydrogen bonding. So these two are extremely important. Okay, so let's take another example. Amines. When you have an amine, a secondary amine, like this is called methylamine. This is diethylamine. So you can always use your gut feeling and your best judgment to name these compounds. When you are cruising through Chem 128A and 128B, you should just pay some attention and use your judgment, best judgment. Sometimes you don't even have to read the book. It's that simple. These guys are pretty polar, okay? These guys are pretty polar, okay? Some other functional groups, like carboxylic acid. Carboxylic acids are made out of these body parts. Carbonyl. On this side, you can put whatever you want, a hydrogen or carbon with hydrogens, of course. It can be HCOOH, it can be CH3COOH, it can be CH3CH2COOH, whatever you want to put. Carboxylic acids, they're super polar. very polar, okay? So they will have a chance to dissolve in water. Let's do an experiment. Let's draw a bunch of carboxylic acids, okay? So I'm going to put COOH, 3 COOHs, and ask you which one will be most likely to dissolve in water, okay? First carboxylic acid will be this. Second carboxylic acid will be, I don't know, this 3-carbon chain. And the other one, I'll make it look like a fatty acid. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 carbons. So carboxylic acid number 1, A, B, and C. Again, this will be a good, it's going to drop a good hint for your assignments. Compound A, compound B, and compound C. If you have to pick one of them to dissolve really well in water, what would be your best pick? Water solubility. We are trying to dissolve it in water. Which guy will be most likely to go into water without any drama? A, B, or C? Connect the dots, what you have learned. What makes a molecule water soluble? Being able to hydrogen bond, having polar groups. Grease is not good. Grease is bad. More carbon hydrogen parts in the body, you're going to be unlikely to dissolve in water. But your chances of dissolving in non-polar solvents will increase. So which dude will have highest chance, the greatest chance to go into water? The very little carbon hydrogen, some carbon hydrogen, and a lot of carbon hydrogen. Answer, please participate. I don't think I look like a scary
Very
person.
little.
Sorry?
It would be A.
So one answer is A. I want to see if everybody else agrees with you. What do you guys think? At least say yes or no. Unmute yourself and say yes or no. Agree with the answer.
Yes.
Yes.
Somebody else?
Yes.
Yes.
Thank you. If I say justify, if in the exam coming week, if I say which one is going to be most likely to dissolve, I mean the questions in the exam are going to be pretty much taken from what we are discussing, what we have covered so far. I try to be very fair, but it doesn't mean I'll give you the same example. I might put like a different question, but with the same concept, maybe another molecule that doesn't have a carboxylic acid, but something else that can do hydrogen bonding. You get the point, right? It may not be the same identical example. Don't tell me that you're so unfair, you're asking something different. Yeah, but it's the same concept, okay? Polar, non-polar, hydrogen bond, ionic bond, this and that, van der Waals forces, grease, non-grease. Okay, how would you justify your answer? Why A is the right answer? This is the perfect answer, and I'll give you 4 out of 4. Well, 2 out of 4 for the right answer, and 2 more points for justification. Why? Simple words. How can you use the minimum number of words to explain and get those two missing points? How would you explain? How would you explain to grab your points? And I told you, less is more. Don't write a story. If you write more than like 1 or 2 sentences, you are wasting your ink or your typing power. How would you justify that?
Most polar.
It's polar. I might take off 1 point. I understand but you need to tell people that you know. Sometimes that's the problem of not getting a grant or not getting a job. They sometimes know that you know, but you need to let them know how much you know. Polar means what? Like solute polar, solvent polar?
Okay,
What are the
so
points?
most polar out of the 3.
it is most polar out of the three. That still doesn't answer something. Is your solvent polar or non-polar? The medium where you're trying to throw these guys in, and you want them to swim comfortably into that solvent, into that medium, is that medium polar or non-polar? You need to tell the audience, you need to tell me that you know that water is polar. So you say, we are testing the compounds in a polar solvent among A and B and C. A is most polar because why? Why is A most polar? I know you know the answer, but you need to spell it out. Why is A most polar? What's the problem when you're going from A to B to C?
A has the least amount of hydrocarbons.
And hydrocarbon is non-polar. So you can say A has least amount of hydrocarbon chain, thus making it the most polar molecule among the three, which is trying to be tested in a polar solvent for its solubility. Therefore, A is most polar. So this is how you need to spell things out. If you just write, if I'm asking you, if it is a free response question answer, then you need to spell it out. Not write a story, but you need to spend enough words to explain what's going on. Yeah, then that does it. You get the point, right? So when the grease goes up, it's less polar. When the grease is less, it's polar. If you don't have any such group, then it's not polar. So I'm going to give you maybe a few more examples, couple more examples, which could be in the question. So another group that makes compounds polar, somewhat polar, is this. Okay, it makes it polar, but not as polar as OH or NH or COOH. It's just a little bit of delta minus and delta plus because you have a carbonyl group, okay? Or something like carbonyl with an oxygen and a methyl group and a methyl group. This is called an ester bond. Not really polar, okay? Not very polar, okay? So between three compounds, let's do an experiment. Let's do a test. I'm going to draw three compounds. This is a real compound that we use in our 129A experiment. So I'm going to color code them. This guy is called fluorine. It spells almost like fluorine. And this is the other one. Okay. Carbonyl here. Okay, C double bond O. And then the third compound, one is called fluorine, one is called fluorinone because it's a ketone, and one is called fluorinone. So the spelling goes like this: Fluorene, and this is fluorinone. None, and this is fluorinol. Fluorine, fluorinone, and fluorinol. Okay. I'm ready to ask you some questions. I'm kneeling down. Which of the three compounds, black, blue, and red, will be most likely to dissolve in hexane? Hexane. We are testing in hexane. Okay, that's the solvent. This is the solute. Solute 1, solute 2, 1, solute 2, and solute 3. And this is your solvent number 1. Solvent A. Which of the 3 will be so happy to go into hexane? A or B, or 1 or 2 or 3?
1.
Shireen, 1. Hexane solubility, one answer is 1. Anybody else wants to take a shot at it? You know what? I can sit down. Why do I have to kneel down? 1, is that the right answer? Are you guys connecting the dots? Anybody else wants to say something just so that we can move to the next one?
I think it's 1 as well.
I can't hear you. Can you speak a little bit louder?
I think it's 1 as well.
1, okay. 1, 1. 1, because it doesn't have anything polar. It's intermediate polarity. That's a little more polar, but it also has a lot of grease. It might dissolve in hexane. That guy will be very difficult to dissolve in hexane. And this is going to be pretty soluble in hexane. What about an intermediate solvent? So what about CH3 OH? This is solvent number 2, methanol, that intermediate solvent, or ethanol. Let's say we are using a solvent that has alcohol as a polar group and also has, you know what, let's make it our favorite alcohol. Now we are testing fluorine, fluorinone, and fluorinol, like no functional, like polar group, a little polar group, and pretty polar group in a solvent that's got an OH group. If I ask you between compounds 1 and 2 and 3, which compound is going to be most likely to go into ethanol? Most likely going to go into ethanol that have something similar to, rub their elbows with. Connect the dots. Does fluorine have much to talk to ethanol with? How about fluorinone and how about fluorinol? Which one will be most soluble in ethanol? Fluorine or fluorinone or fluorinol? Sorry.
Fluorinol.
Camille? Camille says in ethanol, it's going to be number 3. Why did you pick 3, not 2 or 1, Camille?
I picked 3 because the ethanol has a small, well, it has a both polar and non-polar bonds, and so does compound 3. So it would be best at.
How can they interact with each other? What kind of bond they can form?
So they'll have hydrogen bonding between the alcohol groups on the ends, and then they'll also have London dispersion forces because of the nonpolar.
Yeah, London dispersion force. That's the Van der Waals force. Yeah, London dispersion force. Some, not much, but the hydrogen bond is going to really help. Yeah, that's perfect. That's very good. So last question from my end. Then I'm going to shut up and see if anybody has any questions. Water solubility, solvent number 3. Okay. Do you think, well, if you really have to pick one for water solubility, which one would you pick?
Probably 3 again, but I
But
don't
what?
think
I want to hear the but. Esteban, you're talking like a chemist. You're thinking like a chemist.
I just like 3 maybe if you're feeling optimistic, but I still don't think it's gonna go in. Like they're not gonna.
Perfect. Perfect answer. Why? Why, Esteban? Why are you so skeptical? What's the problem?
Just because there's so many hydrogen and carbon bonds, and there's not very. I mean, there's none in water, so.
Perfect. I mean, it's got a hydroxy group. Yes, that's going to do some hydrogen bonding with that. But the amount of grease it's carrying on its back, it's going to screw things up. There's no way that dude is going to solidly in water. No way. I don't think so. I think he's absolutely correct. We can pick 3, but good luck. It's not going to dissolve. But ethanol, by having little grease on the end, will probably dissolve that. This guy in ethanol, do you think this guy has any chance in ethanol or water? Nicked. No, 0. This is a grease ball. It's not going to go into water. Ethanol, maybe not. What if you increase the size of the chain? What if you make this alcohol? This is how you might be tested. What if you take 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. What if you take octanol? If you take octanol, you might get lucky dissolving that guy here. Because it's a little polar, it's got some grease. This guy, maybe, I don't know. That guy, we'll have to test. So this is why 129A, the in-person lab is important. Then we can test these guys in something like octanol. We don't have any experiments like that, but I'm just trying to give you some crazy extrapolation of our experiments or our concepts. So I'm going to shut up. And right now it's pretty late. So I'm suggesting that we do the exam on Wednesday of next week, not Monday. And we can continue our discussion and we can have more discussion and review on Monday. I'm also willing to set up a review session with you guys sometime on Friday, depending. I have a Chem8 review from 5 to 7. We can do it after that. I'm going to send you guys some announcements where I'm going to take your feedback. So regarding this material, I'm going to keep it there for a little while. I'll also take a picture. I'm going to upload the video and the pictures for your understanding and learning and hopefully practice. But right now, I'm kind of opening it up for those of you who still have some energy left and who wants to ask me some specific questions about the assignments. But before we get there, you can see how this is sitting or sinking in your system. Before I forget, let me take a snap. Let me take a picture. Yeah, it's kind of too much stuff on the board, but if you break it down, it's simple. Polar solvent, intermediate polarity solvent, and non-polar solvent. I'm supposed to be talking about crystallization, but I don't want to do that right now. Either we do it I don't want to do it during a review. I'm probably going to do that on Monday after you guys watch some videos of recrystallization. I think it's going to make more sense. You guys watch some of the videos of recrystallization, learn it from the book. I'm going to ask you to really read up some stuff and teach yourself, go through the modules. And then Monday morning at 9 o'clock, I'm going to go over some recrystallization and do a little review maybe during that time to prepare for the exam on Wednesday. I'm kind of 95% I'm leaning toward giving the exam on Wednesday and then Monday. And so we can have the recrystallization talk on Monday, okay? But right now, another 15 minutes or so, I can take some questions regarding the assignments that are due on Friday, okay? So non-polar, intermediate, polar, different types of compounds, non-polar compounds, polar compound, hydroxy group, NH group that makes it polar, not so polar, kind of polar, OH is more polar than NH2 because oxygen is more electronegative than nitrogen. As you increase the greasy part of that polar compound, you're kind of screwing things up by compensating the effect of the polar group. Okay, butanol is going to be much less polar than methanol or ethanol or isopropanol or propanol or tert-butanol. Octanol will be even significantly less polar because even though it has the same tail, it's got a big body that's huge. That's making things worse. Similar things go for different types of acids. If you have a small body acid, medium body acid, and an extremely long body acid, it's going to act like a micelle. Especially if you pull out this proton and make it a salt, then it's definitely going to be acting like a micelle. I don't want to talk about micelle. I love micelle. They're awesome. You can do magic with micelles. Actually, the cell wall is made out of something like micelle. They don't go in a ball like a fuzzy ball, but they form like a little layer. We will talk about it some other time. Then different kinds of compounds, depending upon their polarity, now you should be able to kind of recognize non-polar, kind of polar, pretty polar, but it's got a problem. It's got a very heavy, greasy body, okay? So yeah, use your best judgment. If the greasy body were smaller, then maybe it can be more soluble in something like ethanol. It might even, if it is much smaller, then that guy might have a chance to dissolve in something like, even like methanol or some other polar solvents like acetone. We haven't talked about acetone a lot, but I'm just trying to kind of lay out. So NH, NH2, NH, OH, carboxylic acid, these guys are very polar compounds, okay? Carbonyl, yeah, polar, not that polar. And ester, polar carbonyl, but then having an oxygen next door. It's not a carboxylic acid because there is no H, there is a carbon. So this is an ester functionality. They're pretty non-polar, okay? So with that, do you guys have any questions about the assignments? In that case, what I'll do is I'll erase the board. You want to spend maybe 5-10 minutes on that? Any specific assignment questions?
Yes, I have a question, but it's not like specific about like the chemistry. I guess it's just so I was looking at the assignments and there's a pre-lab, a post-lab, and then like the group assignment. Well, I'm just really confused what the group assignment, like what we're supposed to do for that, because there's like on the parts in the book, it's just doing the experiment, which we obviously can't do the experiment, or answering questions about what we did in the experiment. So we can't really answer those group part questions because I did the post-lab ones, those I was able to do. But I was confused like what we're supposed to do for that part.
Yeah, I should have, it's my fault. So I'm kind of taking responsibility for that. For that experiment, I didn't want to work on that group assignment. Let me look at that. Let me look at exactly what the group assignment was. What was the task to do in group, Shireen?
Well, on the assignment on Canvas, it just said look at part A through E, but that part A through E is like doing the experiment in the lab. So that's why I wasn't sure. And then there's another part A through E that's answering questions about specific things we did in the lab. And then the last part is like the post-lab questions, which I was able to do.
Okay. At this point, I do not want to start any group activity where I assign, like, out of 16 of you, 4 groups with 4 students in each group. Maybe I have a plan for doing that, but maybe a little bit later, not for the solubility experiments. Let me look at it and see what is the best way to tackle it at this point. Because, very honestly, I did teach the Chem 129B lab in spring, like halfway through online, the virtually, but we had already gotten started and finished some of the experiments. This is the first time, so blame it on me for the confusion. Let me see how best we can get the situation under control. I don't want to increase any pain for you guys at this point for this assignment. I want to keep it to the simplest form of activity. So I'm not going to start any group activity for sure, but let me look at it exactly what the assignment is and how best we can handle the situation. I might reduce the number of the questions, and I might ask you to drop some hints and ask you to answer it in a certain different way. I might extend the deadline from Friday till sometime in the weekend, just so that you guys have a little more time to breathe and answer. I know that this is not the only class you're taking. I'm sure you guys, like our son, you're probably taking a bunch of other classes, and everybody is trying to prove themselves, every instructor, by assigning a lot of homework. That's what is happening with our son. So I don't want to increase your pain at this point. Maybe later on, we'll have enough time to inflict more pain in your system. No, just kidding. I want you guys to learn the concept. So let me look at it and let me give you a more appropriate and less fluffy answer. If I try to answer right now, it's going to be filled with fluff, and I hate fluff. So I'm going to give you a more correct and justified answer, fair answer, maybe later on after I review exactly what the questions are. Honestly, I haven't looked at the exact questions. And I was thinking that this is something that's clearly written in the module, but I'm not blaming it on Dr. Muhalski because, you know, this is difficult. Teaching a lab virtually is not easy. Nobody is enjoying it right now. So I want you guys to learn. I don't want you guys to suffer. So maybe we'll extend the deadline beyond Friday. Expect an answer from me sometime today, okay? And then we'll go from there. Sounds good? Anything else? But do you guys get the concept of intermolecular forces? This is very important, right? When you're, you know, as I started this lab with an example, I think I don't know if I said that to you guys or somebody else. When you feel the heat from a hot chili, habanero chili or sriracha or something, and if your lips are burning, by washing it with water, drinking water doesn't help. If you rub your lips or your tongue with a little bit of butter, it actually helps, because the compound that's causing that sensation is very greasy, and you cannot wash it off with water. As simple as that. Water is polar. So you need a non-polar solvent. You cannot drink acetone or you cannot drink hexane. So the best, you know, alternate is butter. It's very greasy. So eat some butter and rub it on your lips and it's gone. You can do that experiment. This can be a lab experiment for solubility, intermolecular forces. Yeah, so that's exactly how it works. So are you guys getting anything out of my blah, blah, blah from my rant? Because I finished these sessions and I sometimes feel really guilty that I just wasted your time. Is it doing you guys any good? Do you guys want to do this or just want to watch the YouTube videos and finish the experiments? Because I know some of my colleagues are not meeting twice a week, they're meeting like once a week, something like that. If you don't like it, it's totally up to you. I can stop these discussions, but I thought that it can also help you with 128A and B, and maybe down the road and clarify some of your concepts. So you can send me some feedback. You can slip some notes under my door if you want to be anonymous. I'm just kidding. But you can send me, you can share your honest feedback. I won't be hurt. Trust me. You can hurt my feelings. Okay. It's kind of like saturated right now. Like, you know.
I think for me, it's more helpful this way because I can watch YouTube videos on my own time, and then this is just better.
Okay. Anybody else? You don't have to praise me. I'm not looking forward to hearing praiseworthy words. So you can say, this is useless.
Yeah, no, I agree. It's been a while since I took like an actual chem class with organic chem, so I think anything extra is helpful, especially you taking your time to do all this.
Okay. 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 Thank you.
I agree. It's more detailed than my lecture class, and I feel like I understand better here as well. And I like how you give like examples, like the lemonade example, like how we could actually apply it into our daily lives. So yeah, I like that.
Okay, and as I said, this is optional, and if you're not sitting in the Zoom class, I won't be hurt. I mean, that's totally fine. Seriously, if you're working and there's no way you can quit that job because you're trying to help out your parents by taking up extra jobs to pay the bills, I understand. That's why I'm doing it synchronous and asynchronous. So I'm asking you guys to be here. If you cannot make it, that's fine. You can watch the video later on. Okay. All right, sounds good. So let's say the exam is on Wednesday. Monday, we'll talk about crystallization. I'm going to upload some videos. I'm going to show you, add a few more links to the videos. The assignments, I'm probably going to push it to at least 11:59 Saturday, so that you have one day, maybe you're not working, maybe you can focus on that. If you have any more questions like Shireen had, send to me and I'll try to figure things out a little bit more. And I'm just being honest instead of BSing with you, like, oh yeah, this is what it means. I really don't know the right answer right now. I don't wanna confuse you and confuse myself. So let's do that, okay? But if you have any other feedback, if you want me to do something else, that's totally fine. Shall I? You guys cannot cause any disruption, but I'm going to throw a review for Chem 8, 5 to 7 Friday, 5 to 7 p.m. Friday. Would you guys want me to send you guys, share the Zoom link with you? I mean, if you are doing nothing, you can sit there. I know exactly who you are. So as long as you don't ask any like lab related question, if you want to be part of that, if you want to just sit there quietly, I don't mind sharing the Zoom link. Shall I do that? Okay.
Yes.
Sure.
Yeah.
All right, I'll share the Zoom link. It might be, the Chem 8 is like kind of like 128A and B, and you remove the cream. So we don't delve that deep. So if you get bored, just check out. Okay. All right. All right. So I'll share the Zoom link. Take care and have a good weekend. Bye.
Thank you. Bye.
Yeah, I really wish we were in person. I think I would have enjoyed hanging out with you guys. It looks like a really wonderful group of people. Bye, guys. I'll share the link once I have figured out the YouTube.